Hi everyone, my name is Christos Koutras and I will present you the first part of the presentation with title Prototype for Scoliosis Brace Simulation. I'm a PhD student in the Multimodal Simulation Lab in the University Rey Juan Carlos in Madrid, Spain. My PhD is part of Rainbow, a Marie Curie ITN network.
Hello, and my name is Katerina Kardash, and I will be presenting the second part of this presentation, Automated Brace Optimization. I'm also a PhD student at Multimodal Simulation Lab, or MS Lab, in Universidad Rey Juan Carlos, Madrid, Spain. My PhD is part of the Rainbow Project and Marie Curie ITN network.
Nice! Now that all of us have presented ourselves, let's start with the motivation of our work. Adolescent idiopathic scoliosis is a complex spinal deformity that impacts up to 5% of children. Severe cases are treated through complex surgery, and using braces is the only way to halt or slow progression with the ultimate goal of avoiding surgery. Scoliosis braces are designed manually, and we research computational methods that could improve their design. Computational design of braces starts with the acquisition of patient images. Then, we design a personalized biomechanical model based on the data of each patient. And finally, we execute a computational optimization to design a personalized brace. So, let's start with it. In the first part of this presentation, I will walk you through the development of personalized torso models, and then Kate will present you the automated optimization algorithm. As I said, our purpose is to develop a personalized biomechanical model of the torso that later can be used for scoliosis brace design. Though, in order to personalize a model, we first need a template one which we can later personalize. Thus, I will start this presentation by describing a template model, and later I will explain how this model can be personalized. In order to build a model, first of all, we need its geometry. Our model consists of the pelvis, the lumbar spine, the thoracic spine, the rib cage, the costal cartilages with the sternum, and the soft tissue. The bones provide the skeletal part of the model, and they are articulated between them, creating a multi-body dynamic system. The soft tissue is coupled with the rigid bodies and simulated with finite elements. We chose to include these parts of the body in the model, as they are the ones that participate in the transmission of forces from the brace to the spine. Let's now see how the bones are connected with each other. All the joints are implemented with a 6 degree of freedom anisotropic joint. As you can see in the example, the joint, green frame, is positioned at the approximate center of rotation of each pair of connected bones. When the bones move, the difference in the translation is given by delta x and in rotation by delta theta. With these two terms, we can define a joint energy E, which penalizes the movement between the two bones. The stiffness values kx and k theta are different for each joint and each axis. For example, the stiffness coefficients are different for the thoracic and the lumbar spine. We take their values from the literature and they correspond to an average person. As already mentioned, we include the soft tissue in our template model. Biomechanical models often focus on the muscles, as they are concerned with the relation between muscle action and the motion of the musculoskeletal system. We are instead concerned with the passive response of the torso to surface forces, and mostly in the motion of the spine resulting from this. We use a non-Hookean material for the simulations, as it represents well the volume conservation of soft tissue. The values of Young modulus and Poisson ratio are taken from the literature. In our case, we transform them to the Lamé parameters μ and lambda. This completes the design of the template torso model. However, before personalizing the model, we want to understand what parameters must be personalized. To this end, we study the sensitivity of the model to its parameters. In order to do so, we design some experiments that imitate scoliosis bracing. So, we get the torso geometry of a scoliosis patient, and we add boundary conditions allowing movements that the brace allows. The pelvis is constrained in all directions and it is only allowed to tilt, while the first thoracic vertebra is allowed to freely rotate but translate only in the longitudinal axis. Then, we apply a force that represents the force exerted by brace on skin. We use a force of 250 Newton, which is the average value exerted by braces according to the literature. Then we compute the model's deformation and we study the motion of the spine. Red means maximum deformation, while blue means that there is no deformation. To formally study the sensitivity of parameters, we compute a sensitivity matrix. This matrix indicates for each parameter what is the change of deformation of the torso. We have identified 6 parameters that can be considered important, and they must be carefully estimated for each subject. These parameters are intervertebral lateral bending, shear modulus, intervertebral axial rotation, intervertebral flexion extension, intervertebral lateral translation, and finally the Lame's parameter lambda of the soft tissue. Actually, based on the sensitivity of each parameter, we can set tolerances for parameter estimation. For instance, if we allow a maximum error of 5 mm in the deformations, these are the parameter tolerances. Now, we can address the personalization of the torso model. We do this in 2 steps. First, we need to get the subject's personalized geometry, and then we need to adjust the model to the mechanical behavior of the subject. For the personalization of the geometry, we capture two low-dose X-rays of the patient, one frontal and one lateral, a procedure which is part of the regular checkup of the patients. We then annotate on them various points that define the position and orientation of the vertebra, their pelvis, lateral rotation, and the scale of the model. Then we leverage the template model I already presented, and we set up a minimization problem with 2 energies. The first one, E-fitting, penalizes the difference between the template model and the annotated points. The second one, E-deformation, penalizes the deformation of the template model, acting as a regularizer. The result is this green skeleton. If we overlay it on the X-rays, we can see that the morphing is quite accurate despite the limited information. We have performed some quantitative validation measuring anatomical parameters and comparing our results with previous work. Our method is at least as accurate as previous methods, but it is more robust and it works just with low-dose X-rays, which minimize the radiation on the patient. Now that we have the personalized geometry of the patient, we can start the parameters estimation procedure. This is currently work in progress, but we can discuss the data acquisition. This is a challenging task, as we need force and deformation data recorded at the same time. To this end, we captured low-dose radiographs from the patients who visited the hospital for their scoliosis checkup. Firstly, a frontal X-ray in order to get the initial configuration of the patient, and then a series of them. During the capture of the radiographs, a force was applied on the ribs of the patient, producing movement in their spine. Their pelvis was fixed in place and their shoulder was in contact with a rigid wall, as illustrated in the sketch. The force readings were registered along with the radiographs. As a result, we captured data that allows us to solve a minimization problem and estimate the mechanical properties of the torso. At the moment, we are focusing our efforts on finalizing this minimization algorithm. Before concluding this part of the presentation, let's see a brief summary. We have designed a template biomechanical model of the torso, and we have performed sensitivity analysis on this model to establish tolerances for parameter estimation. We have developed a morphing procedure to acquire patients' personalized geometry, and currently we are working on the actual mechanical parameters estimation. If you are interested in the details, you might find them in our publications. And now, Kate will continue with the automated brace optimization.
Good day everyone, my name is Kate Kadash and I will be presenting the second half of this presentation, automated brace optimization. Let's quickly overview our objective. The broad goal of my side of this project is to develop a method to produce personalized, efficient braces through optimization. To do this, we need to take the spine model that Christos described earlier, add a parameterized brace to it, and use it with an optimizer that will attempt to find a configuration that produces the stated spine without compromising the comfort of the patient. Now, let's review each of those components starting with the brace. Our current prototype uses the Boston base type design, an example of which is on the left. A Boston base relies on putting pressure on 3 key points of the body. One point, numbered 2 and highlighted in orange on both images, pushes the apex of the curve back into position, while 2 more points, named points 1 and 2 correspondingly, and highlighted in blue, provide counterpressure to keep the posture straight. This approach is perfect for a brace, as it allows us to use the 3 points for parameterization, as pictured here. To parameterize the brace, we divide it into 3 segments, based on proximity to each of the points. This splits the brace into 3 slices which can be transformed independently. When parameters are modified, the associated points move as well, ensuring a smooth transformation. Examples of already transformed braces are on the sides. We choose 3 parameters per each of the slices. First 2 are the x and y coordinate of the center of that slice, and the third is the radius of the cylinder containing it. Since most of the transformation affects the 3 pressure points directly, we can produce notable effect on the spine while only having 9 parameters. Here's a quick overview of how we automatically select the points for each of the patients. The first point is chosen around the armpit or the ribcage area. The second point is located at the apex of the curve. This will be where most pressure is applied. And then the third point is placed around the top of the pelvis so that it presses on the hips. Now that we have the parameters, we need to define an objective function. We need something that's both descriptive and easy to compute. The perfect metric for this is the Cobb's angle, a common method to describe the severity of the scoliosis. Simply put, it describes the angle at which the spine is bent. Here's how it can be computed automatically. First, the apex of the curve is located as the most horizontally displaced vertebra. Then we locate the most angled vertebra relative to the world y-axis, one below and one above the curve. Then we draw lines through the vertebra's y-axis, forming lines VL and VL1 and VL2, pictured here. The angle between those two lines is the Cobb's angle, showing us how much the patient's spine is bent by scoliosis. While Cobb's angle is an incredibly important metric, if we use it as the only measure of effectiveness, we can end up with very exaggerated and frankly unvariable designs, like the ones presented here for your amusement. So we have to introduce a secondary metric that will force our optimizer to produce more variable design. The metric we choose for this task is the pressure exerted on the body when a brace is worn. To quickly compute the pressure, we calculate the norm of contact force exerted by the brace onto the torso. This allows us to easily gauge how difficult its individual design is to wear. On the pictures here, you can see the pressure visualized, and as expected, you can see the hotspots on the 3 points of the Boston base design. So, the complete objective function becomes a combination of Cobb angle and pressure, ensuring the brace is both effective and comfortable. This concludes our overview of the model, and we must now move on to the optimization itself. But first, we need to formulate our goal as an optimization problem that we are going to solve. Let us look at some math. First, we have the input variables. X is the system state of the model, and P is the current parameter set of the brace. The control variable that the optimizer works with is P. The output we want from the optimizer is P star, the optimal parameters, or it is the P that gives us the minimum value of objective function denoted here as G. Note that G depends on both the model state and the parameter P. The function itself is a weighted sum of 2 separate functions. The Cobb angle, which only depends on the state, x, and pressure, which depends on both state and parameters, x and p. Additionally, we set a constraint for our optimization. We require the model to be in equilibrium, or, in other words, the forces in the model must add up to 0. And with all of those elements combined, we have formulated an optimization problem that our project will be solving. Moving on to optimization itself, we must discuss the gradient. Most algorithms make use of the objective function's gradient to find the minimum objective. Here you can see a more detailed expression of the objective function gradient we will be using. Note the partial derivative. While most of the components pictured here are easy to compute, especially since we already have to write the function for g anyway, it's not the case for all of them. dx dp is complex. It could be computed using finite differences, but this is an extremely slow approach, since it has to recompute the model's equilibrium state multiple times per each calculation. We have a solution though. It is called implicit function theorem. To quickly summarize, IFT allows us to replace a derivative of a function with a derivative of a different, multivariable function, provided it equals 0 for the chosen variable values. In our example, we can replace dx dp with the system force Jacobians, f. Because we already require that f is 0, we already fulfill the condition under which IFT applies. This lets us replace dx dp with the following expression, highlighted in red, all parts of which can be computed analytically. And the full gradient now looks like this. While this seems longer and scary, it's actually much faster to compute, since we don't need to rerun the simulation to equilibrium again to get the Jacobians. This lets the optimization run really fast. Let's put our optimizer into action. Here's an animated sample execution starting at an optimized brace that samples the patient's body surface and ending with an optimized brace example. You can see how the optimizer slowly zeroes in on what it considers the best parameter set. Let's see it. Ta-da! At the end, we have a brace producing much smaller Hob angle, while applying only 89 newtons of total force across the whole body. Moreover, because we used IFT, the optimization is very fast, as it only took us a minute and a half to produce these results, and only 10 optimizer steps as well. Here's a small back and forth comparison between the start and finish position of the spine and its Hob angle, so you can see the results way more clearly. To conclude this presentation, let us see a brief summary of this part. We have designed the parameterization for the Boston braces and an objective function that balances comfort of wear and the effect on the patient's scoliosis. We have developed an efficient and robust optimization method for automated design of the brace, and we currently are applying this methodology to a set of personalized models of different scoliosis patients. If you are interested in more details, you may find them in the following publications. Thank you for your attention.